Okay, so the last podcast was looking at having an introduction into what cellular respiration is. It's a way to take energy that is in glucose, and by doing a certain series of chemical reactions, taking that energy out of glucose and turning it into an ATP molecule that is much more user-friendly to your cells and that we can use to do all kinds of stuff. So what this little podcast is going to do is talk specifically about the ATP molecule and why it is the energy molecule that it is. Well, basically that, how it's structured, which we already know a little bit about. Okay, so let's get on with it. All right. We need energy for all of our cellular activities. We've already talked at length about that. Everything from moving around to building our bodies to the active transport across cell membranes, all of that requires energy. So we get that energy fundamentally from, well, this phrase talks about energy coupling. Let's see if we can break down what that means. We are going to use an exergonic reaction. Oh, I don't know, like maybe breaking down food and getting energy out of that, and use that to fuel something that is endergonic, like maybe building up muscle tissue, for example. It takes energy. So we would take the energy released from food molecules and use it to build our bodies, which is an endergonic reaction. So exergonic energy release is used to fuel an endergonic activity. Now, this little set of diagrams here, if I go back, shows how digestion, for example, we break apart these two molecules and as a result we release energy. Then we use that energy down here to do something, maybe causing two molecules to come together to build a muscle cell or something like that. Okay? Now, the in-between step that is missing is that when we release this energy here and then it's used here, we have to take the energy that is released and put it into a molecular form that can be used down here. So what's missing is this transformation step. We need to transform this energy that is released into an energy we can use. And that transformation step is transforming energy into ATP. And so basically what this entire unit is about is how we take this middle step and transform energy into ATP that we can then use to do whatever we want. Okay? So, the thing about our big organic molecules that we need to remember, like glucose, or even stuff bigger than that, but let's just focus on glucose for now, is that they're great. They're very, very useful, but they have way too much energy in them for the body to use. I think we may have talked about this before in class. Let's say your great Aunt Tilly gave you a $1,000 bill, and that's awesome. But if you go to 7-Eleven to buy a piece of gum with that, you won't be able to because they can't handle the $1,000 bill. So what you would need to do is take your $1,000 bill, that is a glucose molecule, and take it to the bank and get them to change it into a bunch of $1 bills, preferably 1,000 $1 bills that you could spend easily anywhere you wanted. Okay? The glucose molecule goes to the bank. In this case, the bank this time, though, is the mitochondrion in your cells. Okay? And gets converted into a bunch of little $1 ATP molecules that can be readily spent to do cellular work. Okay? Uh, Basically, you need to think of cellular respiration that happens in the mitochondria as making change. We're going to convert that big glucose $1,000 bill into $1 ATP molecules that can be spent very easily. Okay? So what are the $1 bills of the cell? Those are ATP molecules. It is really a short-term energy storage molecule. Okay? Glucose is reasonably long-term. Starch or glycogen would be longer-term than glucose. But ATP is very transient because it has inherent instability, which is why it's so good to use for energy, because it can be easily spent, but it's not very good for energy storage long-term because it's so unstable. Let's talk about that. All right, ATP stands for adenosine triphosphate. This is the adenosine part over here. We really don't care what it looks like. This is what we care about. The 1, 2, 3 phosphate groups, adenosine triphosphate. It's really just a modified nucleotide, the same stuff that you would find in DNA nucleotides. Basically, that's that. With one phosphate group, you'd have a nucleotide. We add 2 more, we've got this great ATP molecule. Okay? So, again, Mother Nature is not inventing brand new molecules. She will take molecules that are used for one purpose and modify them for other uses. Okay? AMP is simply adenosine monophosphate. We add a phosphate and we can get ADP. We have ADP, which is what you're seeing right here with the 2 phosphates. We add 1 more phosphate to it and we're going to get ATP. Okay? Now the common transformation that we will be looking at is this one from ADP to ATP and back again. We seldom see this one, but we will talk about ATP and ADP a lot. Now, if we've got an ADP molecule and we want to add a phosphate group to make ATP, that actually takes some energy to do that. It's actually endergonic. But if it takes energy to make it, then how is it not more energy consumptive to make it than it is to use it? That's what we need to talk about. Okay? The key is in these bonds here between the phosphate molecules, and I have just got a great big fat mess. Let's do this. We want to focus right there and right there. Okay? Now, ATP stores energy because, if you will notice, this phosphate group is very negative, as is this phosphate group. Now, they can be forced to form a covalent bond right here, but it is like pushing 2 springs together. You might get them to stick, but they don't want to. They want to bounce apart. Okay? So, we're going to stick that phosphate on there, but it's going to be a really unstable bond because those negatives are repelling each other. Likes repel. Okay? Well, by the time we get this 3rd phosphate on here and we push it towards those other 2, that's really going to be unstable because we've got all these negatives here that are repelling each other, but we're kind of forcing them to stick. So there is a covalent bond, they're stuck together, but they're under a lot of stress, and it wouldn't take much to knock them apart. I wish I had my little ice cream cone, because that's exactly what that's supposed to represent. Okay? All right. So, all those negatives repel each other, so thus every negative phosphate group is a little more difficult to add. But There's a lot of energy stored in each bond, and what's more, that energy is easy to get to because the molecule is so inherently unstable. It's easy to pop it apart and get that energy out. You don't have to put a lot of energy into breaking these bonds at all. And that said, the most energy is stored in that third bond here because this one is under so much stress. It's so unstable. It's the easiest one to break off. Okay? Hardest group to keep bonded is what that says. So you need to think of this molecule as spring-loaded, and it doesn't take much to make it pop apart. Okay? Now, when ATP becomes ADP, as we see here, we've lost the phosphate group, some energy is released. Okay? How much energy is released? 7.3 kilocalories per mole of energy is released. Okay, so we express that usually when we are talking about a change in free energy as a negative to indicate that it is a release. That negative indicates a release. So normally it's expressed as a negative 7.3 kilocalories per mole of energy is released. For every mole of ATP, 7.3 kilocalories is released for use. And that energy can fuel other reactions. One of the main ways that happens is that this released phosphate can be stuck onto another molecule to destabilize it and cause that molecule to do something. So oftentimes what ATP does is ATP comes apart into ADP and a phosphate, and this phosphate is stuck onto a molecule and destabilizes it and makes the other molecule do stuff. If you'll remember with the myosin in the muscle cell, the myosin head, when ADP and the phosphate were stuck onto it, the head went up. It destabilizes this thing and changes its shape. So that phosphate group is inherently a destabilizing feature. Now, an enzyme that adds a phosphate group to something, just so you know, because we're going to see a lot of these, well, we say that enzyme phosphorylates something. So if there's an enzyme that takes a phosphate group from one thing and sticks it onto something else, it's said to be phosphorylating, and it's called a kinase. So ACE means enzyme, kinase means I'm going to take a phosphate from this molecule here and I'm going to stick it onto that molecule over there, and that enzyme is called a kinase. This is said to have been phosphorylated because I took the phosphate off this molecule and stuck it on that one. That's all that means. We'll see that happen as we go. All right. Just understand that your cells cannot store ATP long term and just hoard it. It's too unstable. It won't last that long. So it's too reactive. That phosphate comes off too easily. So if you want to store energy long term, carbs and fats are your best long-term energy storage molecules. Okay? The ATP to ADP transition is basically for short-term cellular work. Okay? So, I've lost my pen. All right. Okay. This is worth noting right here. Working muscle cell, like what we've just learned about, just the myosin heads going up and down to work a muscle, recycles. And that, what I mean is we take an ATP, break it apart, use the ADP and phosphate, and then get back our ATP because it gets recycled. 10 million ATPs per second. That is amazing. Every second, your muscle cells are going through 10 million ATPs per second. Staggering. Okay? Which does explain why we need so much glucose and so much oxygen to make those muscle cells work. We're doing a lot of cell respiration in there. Okay? So, please remember, cells spend a lot of time making ATP to do cellular work. So, the point of cell respiration is to make ATP. But really the point of that is so we can do things, and we can't do things without ATP. All cells use it. All cells use ATP. It is the fundamental energy molecule for all life on Earth. Okay? And what does that tell us about ATP and the evolution of cells? It tells us that ATP was very early on in the evolution of life on Earth. ATP was chosen as the energy molecule. Okay? We're going to stop here, and I hope you have a lovely evening, afternoon, whenever it is you're doing this. And the next podcast we do will be the first of 3 that look at the actual process of making ATP from glucose energy, and that is cellular respiration. Thanks a lot. See you later.